All right, hello everyone. Welcome back to Physical Geology 1403. Today we are talking about Lecture 10, continuing Module 2. Again, if Exam 1 has not been taken, it must be taken. At this point, it is more than a week overdue. We are rapidly approaching Exam 2. You really don't want those double stacking. That's not going to be great because I do start taking off points after a certain time. And, we're actually at about that time for Exam 1, unless you have spoken to me specifically about a circumstance in which you were not able to take Exam 1. Okay. Let's see. Should we start off with an interesting scientific thought? First of all, does anyone have anything they want to bring to the general body of the class? Anything cool? Interesting? No? All right. Well, let me ask you this. If I captured a snapshot of your personality, your consciousness right now, as it is right now, and then compared it to your personality or consciousness tomorrow, would they look exactly the same? What do you think? No? Why?
I don't know. Usually I wake up, sometimes I wake up and I'm just in a different state of mind, I guess. I don't know how much sleep I've
Different
had.
state of mind? All right.
Yeah, I don't know.
But you've changed maybe a little bit between today and tomorrow. Maybe you learned something interesting. Maybe your whole life perspective changes. Maybe you gain a different political viewpoint. Any number of things could happen, right? Yeah. Our bodies are constantly changing. They are dynamic just like Earth is. Our cells constantly reproducing themselves, building new versions to replace old ones. Do you know that none of you have a single skin cell left from the skin you had last year? Your body replaces all of your skin cells basically within the period of a year. Liver cells, heart cells, brain cells, these get replaced. As the old ones wear out, new ones are made. But when it comes to something like consciousness, personality, who you are, what is that? Where is it stored? Brain cells? What about when a brain cell is replaced? Does the new one automatically know what the old one had? Is there some sort of hard drive transfer? It's an interesting thought. Here's an alternative thought, a very compelling one. Do you know what the word quantum means? There's physics, which deals with the laws of the universe, and then there's quantum physics, which basically deals with the interactions of energy and matter at the subatomic level. This is where time and space intersect with each other. When you say quantum, it implies a deeper level of something, right? Quantum computing, have you heard that term before? This is getting real big these days. Computational devices like your phone, laptop, etc., ever since they were invented, operates on ones and zeros. You've heard this term before, ones and zeros? Binary, we call it. A system of ones and zeros to complete a function. A sequence of ones and zeros tells the computer to do a certain thing. We write code. That's what code does. It assembles ones and zeros in different ways to complete functions. Quantum computing, though, has infinite possibility because in normal programming, ones and zeros are set as ones and zeros. In quantum computing, you have essentially bits, which are the ones and zeros over here, think of them as the ones and zeros over there, that until you go to read them could be either a 1 or a 0. This is where things get weird at the subatomic level, at the deepest level that we can go right now. We have made it, it's still expensive, but possible. We've made these before, okay? You can have a computer that has infinite capability because it is working at a quantum level where until you give it a command, it could have either ones or zeros in any order. So what that means is, if you took a flash snapshot of a quantum computer performing a function, you get a readout of ones and zeros. Okay? And that moment that it was performing that function. Because at that moment you took that snapshot, they assembled themselves into those ones and zeros for that function. At any other given time, it's in a constant state of change, being neither 1 or 0. Is consciousness quantum? Is it something that we have at a level deeper than the cells that make our brains? I don't know. But the comparison is very, very interesting. A lot of people are contemplating this right now. How would you even test for that? And if consciousness is quantum, if consciousness goes deeper than the cellular level, because I mean, look at a dog. Dogs can think, dogs can reason, but that's biological function. A dog gets hurt by poking its nose into a thorn bush. It won't do it again because it'll remember. But you can do math. You can philosophize. You can do things that animals acting on instinct or through basic learning cannot. That's what we deem as consciousness, right? Is that at a deeper level than biology or even physics? Don't know. Very interesting thought though, isn't it? Okay. On that note, shall we talk about deserts? What is a desert? Dry. Okay, yeah, I like that. Keep throwing words out. Hot, dry, hot. Okay. Dirt. Isn't Antarctica a desert? Didn't we just agree hot? Okay, sounds like there's a little bit of debate to be had here. Do deserts have to be hot? Do deserts have to be dry? Do deserts have to be one or the other? Does it have to be both? Can we define what a desert is right now? Huh? A little bit of water? Is that something we can agree on? How much water is a little bit?
To the point that the plants have to store the water.
To a point where plants have to store water. Are you referring to like a cactus?
Yes.
Cactus, agave, all of those that store water in their leaves? Do we live in a desert? Why don't we just have cactus? Is the Sahara a desert? How many plants do they have? So wait a second. How come we can live in a desert, but the Sahara can also be a desert, and they are both a desert? Different types of deserts? So there's a whole scale of deserts we're dealing with now? Am I hearing a yes? No? Yeah? Would anyone like to contend otherwise? No? All right, well, that's essentially true, okay? A desert, I'll talk about the definition of a desert in a second, but you can have different types of deserts, clearly, because where we live is commonly referred to as a desert, but then places like the Sahara are also a desert, and they look vastly different. This looks like a jungle compared to that, right? Like the quantity of vegetation that you see here, which we look at and we're like, oh, it's so dry and nasty. And then you go out here and you're like, it's a whole nother level. It's like another planet, right? Yeah. All right, so desert, dry. That's the first word that you said, right? Dry. Well, what does dry even mean? Dry is a very relative term, okay? Dry is a word that implies a lack of moisture, but it's not really scalable. For example, we are drier than the Amazon, but the Sahara is drier than us, but there isn't really a comparative, like a scale of dryness. There is, though, for this thing called aridity, okay? The word arid has to do with the ratio of water in versus water out, okay? Precipitation versus evaporation, okay? So when we typically say something has a dry climate, that's referring to its aridity, okay? So when you have a place that has more water coming in as precipitation and less leaving as evaporation, you have an arid climate. Sorry, where more precipitation, less evaporation, non-arid. More evaporation than precipitation would be arid. How arid is it? That depends on your ratio. There is a scale for that. Okay? All right. Now, temperature is very important here. Why is that? Yeah, typically you get evaporation with high temperatures, right? When it comes to aridity, we're going to separate the world into a couple of different zones here, two, for the purposes of this class. There's a whole range of aridities, like I mentioned. The two we're mostly interested in exploring in this class are steppes, which means, when I say steppe, think semi-arid. Precipitation and evaporation. Evaporation is still higher, but they're fairly close to each other. Okay? Then there's truly arid, which would be an actual desert. Something like the Sahara, where the offset between the two is so high that there's almost never any water available, which is why there's almost never any plants. Okay? Matter of fact, the animals that live in those places, few as they are, have had some incredible evolutionary adaptations. There are, what kind of mouse is it? I forget what kind of mouse it is. But there is a mouse that will ultra recycle the moisture out of its own poop. Okay? Like, so inside the gut of this thing, it never doesn't pee. This animal does not pee. Inside the gut of this thing, it will ultra refine all of the moisture out of the urine and poop that's building up inside of it. And it will, every now and then, occasionally poop out a crystal, basically, of all of that ultra-refined urine and poop together. And this stuff is almost as hard as diamond. Because that is how pressurized and squeezed out all the water has come from it. It's just like ultra-refined, like once a month or so, this thing will just poop out a little crystal, okay? Life has adapted to live in these places really amazingly well. Like, zero water goes to waste. Have you guys ever seen the Dune movies? No? Oh, they're so good. Highly recommend. Timothée Chalamet, Zendaya, Josh Brolin, Jason Momoa. You can't beat it. It's fantastic. Okay. Rebecca Ferguson is in those as well. Okay. So, deserts occur all across different zones of our planet. But I'm going to put them into three areas. Low latitude, mid latitude, and yes, polar deserts. Because you're right. Antarctica, as it turns out, is a desert, a polar desert. What would make it a desert? What did we define a desert as? A place with, yeah, aridity, which is ratio of precipitation versus evaporation. How much rain does Antarctica get? Isn't Antarctica covered in water? How could it possibly be a desert if it's covered in water?
Does it rain? Because it's not evaporating.
Yeah, it's too cold to rain. Rain falls as snow, aka not liquid water, right? So precipitation. But evaporation, hold on now. Have you guys, I mean, this may not be true here. If you've ever lived in a place that gets a lot of snow and ice on the road, you will notice this. It's like 10 degrees outside, but it's a really bright sunny day. You're driving down the road and all the snow and ice around you is steaming. How could that be possible if it's 10 degrees outside? Well, even though the air temperature is cold enough to keep things solid and frozen, all of that bright, clear sky is allowing radiation to impact the top layers of snow and ice and melt just the toppest layer and to the point where it'll evaporate before recondensing again at some point later. That's why you'll see steaming snow and ice in super cold weather. I've seen this so many times. Okay? That's what happens out here. There is evaporation that can occur, and the only precipitation comes as solid snow. Right? So what's our evaporation precipitation ratio? Highly offset. Okay? So that is why places like Antarctica are in fact called polar deserts. Out of curiosity, this could easily wax political, but okay. Out of curiosity, do you guys know what Arctic means? Bear. Arctic means bear. Okay, Arctos is the group of mammals that bears are in. Okay, Arcturus, I believe, is the full name there. So, Arctic means bears. Why was it called that? Where do we find polar bears? If Arctic means bear, what might Antarctic mean? No bears. Bears in the Arctic. No bears in the Antarctic. It's the opposite. Well, maybe not the opposite, but okay. Yeah, bears. Okay, namely polar bears is what it's referring to. Okay. Okay, so that's polar deserts. What about low latitude deserts? Where do we find those? When I say low latitude, do you guys know what latitude means? It's referring to latitude and longitudinal system, which is a way of breaking the Earth apart into different segments, right? Latitudes run horizontally parallel to the equator, up and down from the equator, where the equator equals 0. Longitude lines are perpendicular to that across our planet, okay? But latitude, 0 is the equator. Low latitude deserts occur between the equator and the Tropic of Cancer and the Tropic of Capricorn, okay? Which are about 23.5 degrees above and below 0, okay? So, low latitude deserts, things like the Namib, Sahara, Arabian, things like that, okay? Low latitude deserts. Then we get mid latitude deserts, okay? So the Great Basin, Mojave, Turkestan, Gobi, the Simpson Desert, etc., okay? I'm going to explain why they show up in these places across our planet here in a second, okay? But these are the three categories you break them into. So, in and around the equator, above the equator or below the equator, or the low latitude zones here, the Tropics of Cancer and Capricorn, and then polar. Okay, those are three categories of desert. So why do we get the low latitude deserts? Low latitude deserts form purely as a result of convection forces. Someone remind me what convection is again. I even use his fingers to speak more often than his mouth. Put it into words. Try it again. Circulation, absolutely. It is circulation of what? To where? For how many cookies? Sorry, no cookies. What is circulate? What is convection? Finish that thought, somebody. What happens in convection? Something does circulate. It doesn't matter what it is. We've talked about convection in water, convection in rock. Now we're talking about convection in air. But what is convection? What is moving? Which component of my material? Cold air is moving, but also warm air. Okay, in convection, warm rises, right? You remember that concept? When you heat something up, it decreases density because it increases volume while maintaining mass. So density lowers, warm air rises, just like warm water, just like warm rock. Warm air rises. Where is the warmest part of our planet? What do we call it? The equator. So along our equatorial line here, our warm air is going to rise in the atmosphere. It also happens to be very moist air, very wet air. Why? Because this is also warm, which means it gets the most evaporation. Bingo. So we have very warm, moist air rising up into the atmosphere, and it's going to flow either north or south of the equator. Just kind of depends on which direction it gets pushed, by the warmer air beneath it. Because the higher my air goes in the atmosphere, what's happening to it? It's cooling down. As it cools down, it gets denser again. But it can't fall down right there. It gets shoved to either the north or south by the newer, hotter, rising air beneath it. Okay? So my warm air is rising here, cooling off and getting shoved these ways. As it is cooling off, what happens to the water in my warm air? Condenses. What happens when it condenses? Precipitation, which we call rain. Thank you. It rains. When it rains, it's going to fall down onto the ground. So while my warm air is rising and cooling off and getting shoved either to the north or the south, it's going to start raining out all its moisture. So by the time this cold air arrives over here at the tropics of Cancer and Capricorn, it's also dry air. So I have cold, dry air meeting up again with my continents at those places. It's drying out the land there. It's not bringing rain with it, and the dry air just sucks the moisture out of the ground as well. Okay? That's why we get low latitude deserts. This convection cycle, bringing cold, dry air from the upper atmosphere to the continents, okay, at those zones. Okay, mid-latitude deserts. These happen for a couple of different reasons, all right? So we have some continents on our planet that are actually pretty dang big. We don't have any supercontinents right now. We've had plenty of those in the past. You guys have heard of Pangaea? It was not the first, nor was it the biggest supercontinent we've ever had on Earth. When we take 1404, some of you will take it from me in spring too, I'm sure. We're going to talk about the other supercontinents. We'll talk about the whole list of supercontinents that we knew existed. Okay? But Pangaea was the most recent one. And it had a really big desert in the middle of it. You're talking about the eighth continent. I am not personally an advocate of the eighth continent hypothesis. So the eighth continent hypothesis is, I can kind of show you on that map. It's not ideal. It doesn't really show it very well. Right here, there is this big section of shallower ocean, okay? Off of Australia, under New Zealand coming up here. It's a whole bunch of basalt plateaus and stuff that's shallower than the rest of the ocean around it. And the contention is, okay, but during the last ice age, when we were at the height of the ice age, most of that would have been exposed, wouldn't it? And maybe. Maybe, but I don't think that's sufficient for us to call it a continent. We don't call all of this flooded land off of Florida, Florida, even though it would triple Florida in size during the last ice age. That's part of the Gulf of Mexico, right? So I don't think that we should call something else that is currently submerged under a heck of a lot of water a continent because it might have been exposed previously. That's just me, though. I have not been compelled. I guess the camera didn't follow me. That's okay. For those of you watching this online, the part of the map I was showing here, I guess I can just show you real quick. Camera. Come on now. Camera. There we go. Like, you can't even see it very well anyway, even if you're in the room, but it's over here, okay? This is what, oh my goodness, this camera is not following me very well. Hello? I definitely think it's time to replace my camera. I think this is what the moral of the story I'm getting here. All right, fine. Follow me back this way then. Okay. Anyways, so yeah, that's what you're talking about, right? It's a big thing in the news right now. Every time, okay, so I've taught you guys to be very skeptical of popular news. I've brought this up a lot. Do your own research, do your own investigation. I tell you guys stuff that I have verified or that is sufficiently verified enough for me to believe it, but I always encourage you guys to do your own research from legitimate sources, right? The more people who actually have education in a subject, not journalists, right? Not TikTokers, especially, okay? But the more people who genuinely have an education in a subject, who believe something is true, the more likely you can be sure that it might be, okay? If you have a dozen astrophysicists talking about some new gravitational thing, I'm more likely to believe that than a conspiracy theorist on his YouTube blog, right? Bear that in mind. Where was I going with that? Oh yeah, news. This is something that I call the whole eighth continent thing. That's something I call sexy science. There are two types of science. There's well-thought science, and then there's sexy science. Sexy science is the stuff that all the journalists want to publish because it's the thing that grabs your attention and makes you think, Yellowstone's about to blow up, we're going to die. New species of T-Rex discovered. Changes scientists' mind about everything, right? Those are the headlines everyone likes, like, whoa, really? Sexy science. When you look at it, there's maybe not even that much there. The name of the article may have even grabbed you there. You're like, wait, where was that here? Right? That happens all the time. It's science for the sake of getting attention, not science for the sake of being correct or finding truth. So just bear that in mind. There's a lot of that out there. The eighth continent thing, in my opinion, is one of those sexy science things. All right? But I acknowledge at some point I may be compelled to change my mind because they actually bothered to put out some documentation that makes me think otherwise. All right, so interior deserts. On the inside of these big continents are large tracts of arid landscape. Why? Because they are so far from the coast that they don't get the precipitation from the evaporation of the ocean. The Gobi Desert is an example of this. This whole region out here, Mongolia, Taklamakan, the Gobi out here, super dry. Why? Because it's far enough from the ocean that all of the rainfall kind of rains out here. There's a mountain range here, by the way. All of the rain kind of occurs out here, which is why this part of China, super jungly, super wet, and then this interior portion here is super dry. Okay, so inside of large continents, big deserts. Then there are rain-shadowed deserts. And a rain-shadowed desert occurs where a mountain range blocks the movement of wind. So if I have a big old mountain range and wind is blowing this way, it has to do what? It can't go through the rocks, right? It can't go through the mountain range. It has to go over the mountain range. What happens as it goes over the mountain range? Cools off. What happens when it cools off? Rains. And where does it rain? On this side of the mountains. The side it's climbing up and over. So by the time the air gets over the other side, it's cold and dry. And you get a desert back there. Who can tell me where this is in the world? Well, there's some snow, so I imagine it's a little chilly. Come on. That was a good one. That was a good one. You know it was a good one. Yeah, this is chilly. Okay, so what do we have here? Look at all this green jungle. What is that? Huh?
Green.
I mean, yeah, it's green. What is the massive jungle to the east of Chile? The Amazon, right? The Amazon jungle out here, and then all of a sudden there's all this desert. Why? What's between the two? Huh? The Andes mountain range. These are the Andes. What's happening here? It's a rain shadow effect. So, the wind is blowing out of the South Atlantic, okay, towards South America. Okay? As it hits the Andes, it goes up and over, but rains out all its moisture into the Amazon, which is why there's so much water flowing through the Amazon all the time. There's a rain shadow effect causing all of that prevailing wind to drop its rain out on that side of the mountain range. And then on the other side, the Atacama Desert in Chile. Okay? I'll go back here so you can see that again. Rain, 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 rain. Cold, dry air comes over this side. Desert. Even though there's an ocean there, southern hemisphere, prevailing wind direction is going that way. Desert, right next to the ocean. Okay? So rain shadow effect. Now, both the interior deserts and the rain shadow deserts are caused by the same common factor. What might that be? Which is elevation is made by. There it is! Tectonics again. How many things in our class keep coming down to tectonics? The concept of tectonics is so important in geology. It changes a whole bunch of stuff. It creates a lot of the things that we see and observe on our surface and underneath of it. Okay? Hope you're catching that theme here. All right. So what sort of processes happen in the desert? Weathering still happens. There may not be a whole lot of rain, a whole lot of water, but you better believe weathering is still happening. How can weathering still happen in the desert? What might be the primary source of weathering in the desert? Or the most consistent one, I should say. Wind. What do you think? Is the constant 364 days a year effect of weathering from wind more or less powerful than maybe the one day of rain a desert might get? Wind more powerful? Who thinks so? Raise your hand. Water more powerful? Who thinks so? Raise your hand. Wow, I'm proud you're not abstaining from a vote. Oh, are you tempted? You're tempted. What do you think, Genesis? Water? Okay. Water wins! Even if you only get one day of rain a year, it still does far more weathering than the entire rest of the year of wind combined. Why? What does water have that wind does not? It carries things. Viscosity is what we're getting at here, right? Right? It's way thicker than wind. Wind is just air. If I sat here and blew on this, how long would I have to blow before it falls over? Huh? Till I pass out? Well, let's assume I'm an infinite wind machine. Yeah. It won't. But if I got a garden hose and I turn it on a full blast, am I going to knock that thing over? Yeah, it's going to knock over. What about a fire hose? Right? Blast that thing across the room. Go right through your head, probably. Those things are powerful. You ever seen a fire hose in full action? Dude, those things are crazy. All right. I was about to make a comment, but then I realized it would make me seem really old. So I'm not going to do that. All right. So yeah, water has much more of a weathering effect and eroding effect than wind does, even though the wind is far more consistent throughout the year. Okay? When we do get rain in a desert, it will often fill up these bodies, these areas that are usually dry, and you may not even know they're there. So here's a before and after picture. Here's the before, here's the after. You can see, now that you know where that is, you can see where the dry stream bed is, right? This is what it looks like for most of the year, and then when it rains, it fills up with water, just for a little bit of time, just until that water runs away or evaporates, okay? We call these ephemeral water bodies. Ephemeral means short-lived, okay? Ephemeral bodies of water, ephemeral streams, ephemeral lakes, ephemeral ponds, etc., okay? Okay, now as for that wind, even though it's not as powerful as the water, it still does a lot over the course of a long period of time. Rarely is there a desert without some strong force of wind. Okay? So water and air have a few things in common. Both are fluids, right? Gases are fluids. You're familiar with this concept? Not liquids, fluids. Okay? Gases and liquids both are fluids. Solid is its own thing. So, that being the case, both can be moved by changes in pressure and temperature. Okay? Wind is caused by a change in pressure, which in turn is caused by a change in temperature. Hot air is a high pressure zone, cold air is a low pressure zone, and hot air moving high pressure into low pressure makes forces of wind. Okay, there's your meteorology 101 for the day. So as this wind is blowing, the stronger it gets, the more energy it contains. Water does the same thing. The stronger it gets, the more energy it contains. Okay? When we have lots of water with a lot of energy, it can pick up a whole bunch of stuff. Wind can do the same thing, but here's the difference. Water has this aspect called cohesion. What was cohesion again? Yeah, they like to stick together. So when I get water, you usually have some body of water like a stream or river instead of being spread out all over the place. Air, though, doesn't care. It's gas, no cohesion. So I could put the same amount of energy into a quantity of air as I do with a quantity of water, and that quantity of water is going to direct itself in a straight course together, keeping all the energy confined to a space. Whereas the air won't be confined to an area. That energy gets spread out through an entire mass of air. Okay? So water has much more of a carrying effect with that energy than air does. So that being said, strong enough wind can still move pretty big things. I don't suppose any of you have ever lived through a hurricane. I've been through 3. Okay, 2 in Louisiana and 1 in Japan, except we call them typhoons in Japan. The one that I had in Japan was by far the most destructive. We're going to talk about coastlines in our next lecture. I'll tell you more about that experience then, but it was highly destructive to my community. I'll just say that right now. Winds are capable of picking up and moving pieces of houses, ripping houses apart and carrying the pieces away. Tornadoes, right? Tornadoes capable of doing that. That's wind. Okay. So our wind, just like our water, can carry a bed load and a suspended load. The other thing water had was a dissolved load. You can't really dissolve something in air, right? You can in water, you can't in air. So it has a bed load and a suspended load. Can someone remind me what the suspended load is again? What does suspended load mean? Well, it's not floating. It's being carried in the current, right? In the case of water, the current of the water. In the case of the wind, it's in the air. right? The snowstorms, the sandstorms that blow through our town every now and then. Do you know what those are called, by the way? Do you know what the word for those is? They're called haboobs. Yep, sandstorms are called haboobs. So when those haboobs move through town, right? And for some reason, we always seem to get those whenever I'm at Walmart. Like, I'll be walking into Walmart and I'll just see this big orange cloud like blowing into town. I'm like, oh, I better get in there, right? Or I'll be walking out of Walmart and all of a sudden there's sand in the air. And it's like, what is happening? What happened while I was in there? Right? For some reason, that's the only time it ever happens. Maybe I just spend too much time at Walmart. Might be an indicator. Universe is telling me something. Get out! That's suspended load. All that dust and sand in the atmosphere, that's suspended load. What about bed load? What is bed load? There you go. Moving along the ground. Perfect. Thank you. Okay. It's moving along the ground. What does your hat say, by the way?
Lazy wrench.
Lazy wrench. Oh, I knew it said lazy something. I was like, what is this? Okay. Yes, moving along the ground. The energy of the wind is not sufficient enough to pick up a particle of that size, but it is moving it down across the ground surface. Okay. The movement of bed load across the surface, this is usually sand for the most part. We call that movement saltation. This has nothing to do with salt. Okay? Saltation is a Latin-based word. I don't remember exactly what it means, but it has something to do with movement. Okay? Saltation is the movement of sediment across the ground surface under the influence of wind. Okay? When that material is moving across the surface, it's getting pulled from one place and taken to another. When small particles are completely removed from an area, we call that deflation. So you're losing sediment from one place, that's called deflation. When an area gets enough deflation, so all my, say, silt and clay and sand-sized particles are removed, and only the bigger pieces are left, the pieces too big for the wind to move, we call that a desert pavement. And you'll see this, if you ever go walking through a desert, I've seen this plenty. Usually I see this a lot whenever I was walking through the Badlands of North Dakota, South Dakota, and Montana a lot of the time, okay? I'd just be walking, looking for dinosaur bones. In this case, I was always looking for dinosaur bones. And all of a sudden I go from sandy landscape to crunch, 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 just a couple 100 yards of nothing but gravel and big rocks. I'm like, well, where'd all the sand go? It was deflated away, leaving behind desert pavement. Okay? That's what we call that. Some other things that we can see as a result of the movement of this wind. Ventifact. A ventifact is when a piece of rock is exposed to the wind. Now, this powerful wind is carrying stuff like sand and silt and clay, and its suspended load and its bed load. What do you suppose that's going to do to an object over a long period of time that's exposed to all that stuff? Yeah, are you familiar with the concept of sandblasting? Sandblasting is when you take, it's essentially, think of it as like a snow blower, okay? Except instead of blowing air to move snow away, you're blasting sand to break things off of an object. You would sandblast a car to take the paint off of it before you repainted it. You would sandblast a bathtub to remove lead paint to repaint it, things like that, okay? So this wind is essentially sandblasting all of these objects, shaping them, smoothing them out. And you get these aerodynamically shaped, this one's kind of in this triangular shape because it's pointed in the direction the wind is coming because that's how aerodynamics works. Okay? It's been shaped and smoothed out into that shape according to the direction of the wind. Okay? But if you pick this thing up, I've done this a lot. I found a lot of ventifacts out in the wild, okay? But you pick up this really smooth-looking rock on the surface and you pull it out of the ground, the underside of it is all broken and blocky and chunky and dirty, just like a normal rock would be, because only the part that was exposed got sandblasted, okay? And then this is a yardang. No, Dr. Seuss did not make that word. Okay. This is a Pakistani word. Okay. A yardang is kind of think of it like this: a large geologic feature that has been shaped by the wind. Can you see this odd shape? It kind of looks mushroomy, huh? What observations do you make about this? How might the wind have shaped this? Yeah, it's narrower at the bottom. It has kind of this stem or trunk here. Why would that have happened? What was happening to this that caused the bottom to be narrower, smaller than the top? Okay, well now we're making another observation. You're saying that there is a shape here. Is that what you're talking about? You're talking about aerodynamics now. Okay, so now we've identified both of the things I wanted us to talk about, but now we need to dive into both of them. Let's go to Jose's comment first, okay? He's right. Do you see this aerodynamic shape here? Why is that shape aerodynamic? Yeah. Wait, which direction did you say? That way? Who agrees with him? Is the wind blowing this way or is the wind blowing that way? Who says right to left? 1, 2, 3, 4. Who says left to right? None. Got it. Okay. Let's go back to airplanes. You guys have been on airplanes. We talked about airplanes. How many of you have been on an airplane? How are the airplane wings shaped? What direction is the front of the airplane? Yeah, the front of the airplane's over here, right? So then, as my airplane is moving forward, what direction is the air flowing? Why are airplane wings shaped like that? Physics. Okay. So as my air is moving over the airplane wing, it's bulkier at the front, narrower at the back. As it crosses over the middle of the wing, and my wing starts to narrow down, my air speeds up on the second half. So it's going over the top. You can clip that if you want, people. I guess if you want, it'd be a fun video, I guess. Just maybe go for hours on end. Okay? But that's how this is driving. This is how an airplane stays in the air. It is making air pass over its wings faster on this end than it did on that end, creating uplift and speed. This is how they slip through the air. This is an aerodynamic shape. By the way, if I turned this right side up, what shape does that make? Huh? Like a drop of rain. Things naturally form into this aerodynamic shape under the influence of moving air. So, I ask again, what direction is the air blowing? Is the wind blowing in this? Left to right or right to left? There we go. Now we know it's going that way. Okay, so now this helps us a little bit answer the second observation. That was Jasmine's. That it's narrower on the bottom than it is at the top. Why is it narrower on the bottom than it is at the top? Elaborate. Why would sand be a factor here?
Because it's on the ground.
And what do we call that? Bingo! The bed load is being pushed along the ground. It's sand. Heavier particles, more energy, right? So the silts and the clays and the things in the suspended load, that's what's slowly been shaping it into this aerodynamic shape. But why is there more weathering happening down here? The heavier particles being pushed along the ground level are slamming into the bottom of my feature. And again, how do I know what direction the wind is coming from here? Which side of this has the most weathering? So the wind must be coming from that way. Huh? Pretty cool. Look at how interpretation savvy you guys are getting. I love it. All right. All right, now that bed load, that sand that's being pushed along the ground, it's traveling in a certain direction. That wind is pushing it. Eventually, that wind pushes it up into these kind of piles. Okay, so you pile up all the sand, and this pile of sand starts moving across the surface. You know what we call a pile of sand getting pushed by the wind? Dunes. Now, dunes have a very characteristic shape. Generally like this. Wind's blowing this way. Sand is getting blown up this very low angle slope. But then once it reaches this point, something else takes over. Wind is no longer the driving force pushing things up the slope. Now that we are on a downslope, what takes over? Gravity. This is called our slip face. So sand is slowly getting pushed up our slope and then falls down the slip face. So you can see here's the slope, slip face, slope, slip face. Here's the slip face right here where you can see sand falling off of the edge of the slope, moving downhill. So what happens over time is our dune gradually moves off in the direction that the wind is pushing it. Dunes move. They migrate. There are places out in Utah, southern Utah, where I went when I was doing some studies for my undergraduate degree, for my bachelor's degree. Dunes are constantly moving through towns out there. They move so fast that you'll go to sleep and you'll wake up and a dune will have migrated over the road in your town. They have specialized snow plows specifically for getting sand out of the way, not snow. Okay? Something they have to deal with. So, this is how a dune will move and how many other dunes will follow. Okay? All of these are migrating in that direction. Sledding? With a razor? Oh, you mean like with like a four-wheeler? Yeah. I've gone four-wheeling. I have not gone, like, you know how you can put sand tires on like a dirt bike? Like paddle tires? I haven't done that. That looks really fun, but I haven't done that. I go sledding out in Monahans with my kids a couple times a year. That's fun. We'll talk about the Monahans dunes in just a second. Okay? Let's talk about the different types of dunes there are. Barken dunes are what, when I say dune, you're probably going to think Barken dune. This is that characteristic dune shape. This is the one that we see up here in this picture. Okay? Barken dunes have this crescent shape to them. Okay? Where here's our slip face here in the middle of our dune, and here's our slope right there. Why the crescent shape? Why do they make that shape? Say that louder, I'm sorry. I see what you're saying. And the answer is, in part, because of the aerodynamic shape of that dune. Do you suppose it takes more or less energy for wind to push sand up this slope or around the slope? More to go up. But, I mean, wind doesn't get to choose, right? Wind doesn't make the choice of, I'm going to push this up or I'm going to push it around. But what happens is, as the wind is pushing equally on all of the sand in this dune, the sand on the outer edges goes a little faster than the sand going up the slope. And so our dune stretches out more on the outer edges, making that crescent shape. Then we have transverse dunes. So in a Barken dune, this is what you'll get when you have sand, but not very much of it. So you get these individual dunes that are moving independent of each other. Okay? When you have a lot of sand, we call these sand seas. Okay? You will get transverse dunes. What does this look like to you? Yeah, these look like waves on the ocean, don't they? That's essentially what they are. Picture, if you will, instead of each molecule of water in the ocean being subjected to the energy of the wind and therefore pushing up into waveforms that move across the surface of our ocean, each individual grain of sand acting as a molecule of that water under the same energy, but because they are so much bigger, they move at a much, much slower scale. So while a wave, the wave energy may traverse an ocean in a few days or weeks, depending on the size of your ocean, it would take millennia for a dune, a transverse dune, to move across. Okay? Transverse dunes. Plentiful sands, lots of sand. Sahara. Think Sahara here. Sahara used to be the bottom of an ocean. Do you guys know that? Until only a couple dozen million years ago, it used to be the bottom of an ocean, which is why it's covered in sand. It used to be the bottom of an ocean. Cool. Then we have Barkenoid. Now, Barkenoids are kind of a combination of the two. So you have kind of a moderate amount of sand. What happens here is my transverse dunes start to form, but they form because multiple Barken dunes kind of merge side by side with each other. So you get obvious crescent shapes, but they're linked at the edges and kind of make that sort of shape. Barkenoid. Any questions so far, by the way? I haven't really stopped to see if you guys have any questions. Any questions about anything so far? Okay. Then we have longitudinal dunes. Now with a longitudinal dune, you get your same Barken dune, but wind forces are much, much more powerful, which means that the edges stretch further out in front of the main crescent shape, the main body. That's longitudinal, okay? And depending on any change in wind direction, my longitudinal dunes may actually be kind of asymmetrical. Then we have parabolic dunes. Parabolic dunes have that same crescent shape. But there's a catch. Now, this is my slope, and this is my slip face. It's inverted. The crescent is now pointed towards the wind direction, not away from it. What might make that happen? Nope, we're assuming a consistent wave direction, a wind direction here. Sure, yeah, you can read that. There's vegetation, but what does the vegetation do? Its roots hold sand together. So if there's vegetation holding sand together, is vegetation going to hold deep sand together or shallow sand together better? What do you think, Nathaniel? So let's say grass. Grass is going to hold, well, any plant really, but grass is going to hold deep sand together easier than shallow sand? Who agrees? Who disagrees? You guys want a fist fight? Oh, you don't disagree that much, huh? Okay, fine. The edges where my sand is shallowest are going to be held together by vegetation easier than my body of deep sand in the middle. So my body of deep sand now is moving faster than the sides being held together by vegetation. So my crescent has flipped. You following that? Great. That's a parabolic dune. And then the last type is called a star dune. With a star dune, you get your sort of crescent bark and dune shape, but there's multiple crescent shapes. Why are there so many crescent shapes? This is where changes in wind direction come in. If I have wind that comes from this direction in the morning and that direction in the evening and that direction at night, or whatever the case may be, it's going to make my crescents push in different directions and congregate together like this. These are what most of the Monaghan's dunes are. They're a mix of Barkin dunes and star dunes for the most part, from what I've seen. Okay, which is why you can climb up to the top of one and be like, okay, so I can sled down that side or this side. This side's shallower, this side's deeper, so on and so forth. But there are multiple faces that you can slide down on the dunes out there. Okay, no questions about dunes? So that explains what happens with the sand. But what about the silt and the clay, that suspended load that the wind is carrying away? Well, we call that stuff loess. L-O-E-S-S, loess. That loess can be blown very far. Look at this picture right here, for example. This is the western edge of North Africa. That's the Sahara Desert. You see all of the dust being carried by the wind here? Where's it getting up? Where's this? Who can tell me where this is? Yeah, Central America. That's Yucatan right there. Cuba, Florida. Panama's down here. Yeah, that dust from the Sahara is getting blown all the way across the mid-Atlantic and ending up in Central America. Matter of fact, there are days where the air quality in Central America is so bad, so dusty from all of the stuff blowing across from the Sahara Desert that people have to wear masks out there. This stretch of ocean, the bottom of the ocean here, we've taken samples from down there. So much Sahara dust out there. Okay? So it can make it really far. But here's the thing. As much as it sucks for the air quality, people trying to breathe that stuff in, this loess has some pretty unique characteristics. How much vegetation is there out in, say, the Sahara Desert? Barely any. Which means there's no plant life breaking down that mineral content in the soil. Which means, in turn, that if I were to mix that mineral content with all of the other requirements, all of the other properties that I need to make a soil, it makes the richest soil on Earth. And there is one place where that happens. Where, in combination with the Sahara mineral content, this loess, could I add water, air, and organic content? Who's familiar with East Saharan geography? No? No students of East African geography here? Is my camera going to follow me? No, it stops right there. All right, well, I'll show my physical students here and my online students. Look at a map of East Africa. What are you going to see? Who can tell me what this river is? It's the Nile. Yes. You've heard of the Nile River in Egypt? Why is the Nile so famous? Okay, you know what? That's true. That's true. That's one of the reasons it's famous. It's the only river in the northern hemisphere that flows north. Okay, the rest of them flow south towards the equator. But that's just because of it's flowing downhill, right? The Nile flows downhill from Central Africa out into the Mediterranean. But why else is the Nile famous? Yes, bingo. It's one of the first places that civilization began. Why? Picture, if you will, 7,500 years ago. Migrant, nomadic peoples, tribes of people wandering across northern Africa and northern and northeastern Europe and the Middle East. Just nomadic groups of people, not really any established civilizations quite yet. A few, but not very many. They find this river, and along the banks of this river, they find plants growing. Like, oh, how delightful, a river. There's some plants. Let's stay here for a season. We'll plant a few things. We'll leave our animals to eat some stuff. And it's so nice. They have running water. The soil is incredible. They've never encountered soil anywhere else on their travels that can grow things as well as this can. Why? Because of the incredible quality of the mineral content blowing into that river from the desert. Okay? So they decide to stay for another season. They grow more crops. Then they realize, wait, guys, why would we ever want to leave? They cease to become a nomadic people and become an established group. They make a community. That community grows into several communities stretching up and down the river. Those communities grow into cities. Those cities eventually unite and become the longest standing, most powerful empire this world has ever seen, the Egyptian Empire, which lasted for 5,000 years. All because of one reason. They started off as an agricultural community, and because of that incredible agricultural base they had, they were able to establish vast armies and conquer most of the other civilizations in North Africa and the Middle East for a while. The Egyptian Empire was all over the place over there. Okay? It took the Romans to bring them down for that last time. Okay? And they lasted that long purely because they were able to feed an incredible quantity of people off of the soil that they got from the Nile, which comes down to the simple geologic fact that the loess from the Sahara was prime for that purpose. Interesting. Any other geologic setting in the Egyptian Empire would not have formed. Okay. So we can get, in the desert, alluvial fans like this. This is clearly a desert, but what do you see here? Look at all of these alluvial fans forming at the base of this mountain range. Why? Well, even if there's only one day a year of rain, what's that rain going to do? Erode stuff downhill. And when it reaches the downhill part, what do we call it? An alluvial fan. So here we go. Alluvial fans right there. Okay. Then, when we have bodies of water that form in a desert and then evaporate away, they will often leave behind flat expanses of sediment. We call these playas. Okay? Often these are covered in very fine silts and clays, but there can also be evaporate minerals. Okay? So we're going to see a lot of gypsum and salt out on these playas as well. Okay? This is a playa out here. I've driven over many, many playas in Utah on my trips out there. Okay? Lots of these in that part of the world because it was, like I said before, a very large lake that then dried out. Now, I know what y'all have been thinking. You've been considering to yourself, okay, this is all very useful information, but I want to know what happens to a volcano when it's in a desert. Don't worry, I've read your mind. I'm going to answer your question, okay? We call that an Inselberg, okay? When a volcano gets trapped, essentially, inside of a desert, or I should say a desert forms around my volcano, it will make this. It's the closest comparison I can make here, and go with me on this. Have you ever put like a Hershey's Kiss in your mouth and like sucked on it for a second and then pulled it out? It looks like a half melted Hershey's Kiss. It's kind of sad. It's like, really? That was a volcano? That's unfortunate, right? But it's clearly breaking down, right? And look at this. You can see the buildup of dunes on the other side that tells you what direction the wind is blowing, right? It's coming from that way down this way. No dunes down here, all dunes up there. The dunes are blowing up against that side of the volcano. They're collecting over there. None of them have made it around the volcano over here. It's an Inselberg. No. So this one is extinct. This is an extinct volcano. Could the live volcano have this happen? Yeah, definitely could. There are volcanoes in desert areas, but we would not necessarily call it an Inselberg at that point, I don't think. Inselbergs, to my understanding, or at least in the definitions I've heard the word used, refer to the ones that are part of the weathering and erosive effect of the desert. Any other questions? No? All right. Well, then I will end the lecture here. Oh, look at that. It's 11 o'clock. Like on time today. Okay, so I'm going to end it here, and that gives us an hour and a half or so for lab time.